Okay. So we're live. We're 3 minutes late. I can deal with that. Okay. So it looks like no one's on at the moment. So I guess I'll still do an announcement. People can play back and listen to the announcement. Um, let's see. Looking at the review, let me look at our. So a question went out on the community pages. I mean, only like 30 people actually see this, so it's not a big issue. So let's go see what how I did a poll today. Yeah, I did a poll of what people would be interested in an FPGA. Um, let's see. We'll probably find a way to bring this up. Okay. We don't even know how to do that. So if we do like a new incognito window, right? We go to YouTube FPGAs. Come up. Community, I guess. Sure, community. We can vote. Oh, well, this way we can keep it a secret. So, we had 15 votes. Vitus AI neural networks got 47%, so this is number one. Crypto mining got 7%, so like one vote. I was surprised by that. I'm not so especially topic of this video. I thought cryptocurrency would be more interesting. Looking at doing a USB-C 20 gigabit driver, that was 20%, so that was good. And then SpaceWire router got 0. Kind of sad about that one. That would have been a fun project. Hobby projects. So looking at kind of like the open source boards, looking at kind of fun little keyboard based FPGA, like handheld battery based FPGA or keyboard based projects with maybe like a Wi-Fi chip in it or something. Could do some interesting stuff with that. Okay, so with this, I guess we're going to do a little bit more looking at Vitus AI. And let's see, if we're going to talk about the schedule going forward, the schedule going forward has we'll put Ubuntu on the ZCO 104, then we'll do a DPU design, then we'll use the camera that comes with the ZCO 104 as part of the DPU design. That sounds like it's gonna be a lot of fun work. We'll have to see how we can process that. I'm not sure. I'll have to look at. Oh, that's a USB camera, so that's not too hard. Maybe we can look at doing some hardware acceleration, image processing with our stuff. But that will be about it. So yeah, today we're going to be looking at the SHA256 design running on the RD device. We did this before. We had issues with the TCP server, or whatever server. I'm not sure if we did TCP or not. Is it main? So this is an Echo server. So we do have DHCP. So we're just going to go ahead and run this on the board. Do we change the Ethernet? Or we change the baud at all? I'm curious. Do not change the baud to the default. Okay. We have the Terra term in the little window in the screen. You see on top above the keyboard. Oh, that's a terrible thing. So whatever. Let's see if we can like get camera. Particularly like this position. See. Yep. So let's see. I have to reorient it. But let's try to see how well you can see the UART messages. It's terribly reflective. Sorry, maybe we can like go a little bit upper. You wanna see any LEDs we can see? That's about as good as we're getting. Okay, let's rotate that image so it's not so hard for you. There we go. Reverse. There we go. So yeah, let's go ahead and see what our run configurations look like for this. This is just a very simple Echo server. So I want to make sure we're working. We're going to do a little bit. Yeah, let's go ahead and program the FPGA, reset the entire system. Fly. Run. Hope it runs in the first time, right? Yeah, me too. Oh, FPGA programmed. You can't really see the progress. I'm sorry about that. There we go. Link speed is 100. Looks like we're getting messages. That should be connected. Yeah, that one's disconnected. Okay, we have an IP. So TCP echoing at started at port 7. Okay, so forward IP is 1.8. So let's go ahead and do a new connection. We're going to do telnet, right? Port 7. Port 7. We want to do 8. 8, right? Right. I think that's what we want to do. We have a new window. Okay. So we have this new window, and I believe we go to terminal. We receive, we hit auto. Hello. Oh, we need a local echo. That's what we need. Terminal, local echo. Hello, I am Wilson. Cool. Okay, that's working. Let's see if our other design finished. Bitstream complete successfully. Okay, so this is the one. This design is the one that has the code. Has the I'm putting bar controller. The coprocessor, the minor coprocessor, which is using AxiStream, and we have that being monitored. So we're going to go ahead and open the SDK. I did have to rebuild this to make sure it matched the reset. We're going to have to update the SDK, but we're going to try to get Echo Server working on this. And if Echo Server works on this, then we can go ahead and do their minor application. Okay, so let me see. Does this state which modify BSP settings, pop hardware? Can we change the specification? I'm just curious. Can I change the UART settings in here? Change the UART. Okay. The design one wrapper. And you can't go and hardware specification. Oh well. I think we can change which BSP we are. Let me see if we go to source. Change reference BSP. Okay, so we can go generate a BSP and change reference BSP. Cool. So now we're going to go back to our Arty project right here, and we're going to go File, Export, Hardware, include Bitstream, look at the products. Yeah, we're going to override it. Then we go back to this SDK, and it should be Design 1, Wrapper, Hardware, Platform 1, change. Yes, so we're going to update that one, regenerate the BSP, and go for it. Oh. Then I'm going to get FPGA Miner working on it. Okay, cool. And can we saw that this one was the one. Okay. So we want to that project's building. Binaries. Clean project. Okay. And no. Build. Okay, that worked. So run configurations. We are going to debug echo and design 1-bit wrapper, auto detect application, echo, reset processor. Let's do it. Boom, boom, boom. Apply and run. Was held in reset. Oh, we were having this time issue before. Why are you being held in reset? So something is different between these two designs, and we gotta figure it out. So the only thing I can think of is this sys reset. Make 7. Oh, garbage. Where is this reset on this mix 7? Ah, we are just using the straight up reset pin. Let us just straight up use the reset pin. Polarity is this? Polarity low. Polarity properties. That's definitely polarity low. Right here. Active low. Okay, cool. So let's come back here. So this is bad. Where is that on this other design? Okay, where is the debug module? Debug module. This is going to the processor debug module. Microblaze. Microblaze, debug reset. Microblaze. Where was that other? Do we have a where's this going to? Oh, right there. Microblaze debug reset there. Good, good. And board. Where's the reset signal? Is there a reset board? That's apparently it's there. Yeah, do it. Okay, we have a reset. And let's put this on the clock. We have this clock. Go ahead and put a reset on this guy as well. To do clock outputs, clocking options. Let's do a reset. Why is it so hard to press buttons in these GUIs? I have to make the screen smaller for streaming, and man, sometimes it's just hard to do things. Okay, regenerate. Validate and save. Okay. So, Clock Wizard. Well, that's clearly my fault. We should have active low there. Sorry, completely my fault. This is active low. Oop. Oh. Once it's validated, we'll rebuild it real quick, and then we have to go find where I grab this repository. Yeah, I'll have to go over here, maybe. Let's go over here and find it. Okay, so hopefully I can talk and interest you why I rebuild the design. Hopefully it doesn't take too long. I'm going to try to find where we originally pulled out that repository. Why this is building. Generate bitstream? Yes. Didn't take too long. See, do we have it under here? FPGA miner. Okay, cool. So, like we did before, let me see. If we edit this with Notepad++, is it not that one? Close all but this. Bring this on over. Okay, it looks like we can just run this, right? So we're gonna just run CPU test. So control click, shift click, open PowerShell here. CPU. Oh, doing it in a separate window. That's a first. Let's do it in this one, Python 3 CPU. Okay, apparently it's gonna sit there for a while, so we'll let it sit there. Okay, put that in the background. Yeah, we should totally say something. Okay. And then in the example and minor, they have the server connecting to FPGA, socket stream, mine, main, keep alive. I'm gonna have to change that. That's the correct, and that's the default. Sure. Um, okay, so I'm not sure what keep alive is. Keep alive if keep alive equals false, else true. Keep alive if not. Uh, mm. Okay, so we'll, yeah. So going back here, what we got? It's still running. Oh, there we got hash. Great. Nice. I just love that word. Nonce. Okay, that's great. Going back to our project, how are we doing? We're in synth design. Log of synth design. Now, sorry, synth design complete. So we're moving over to implementation. Great, great, great. That will be done before we know it. Whew. So, anyone has any questions? Chat's been quiet so far. I will say hi or wave. A wave. Or that changes the name. Wave. Wave at the chat. I see you people watching me. Feel free to join in. So I guess we'll play a quick sitting game, or I guess we'll review code. Probably the smart thing. So we go back to the SDK, right? This is unhappy for something. Why is this unhappy? It does not tell me why it's unhappy. Probably didn't build last time. So they just redid the Echo server. So their code should be very, very basic. They just went through the Echo server. They should have DHCP on. DHCP is on, so this should run exactly as the Echo server. So we just got to get the Echo server working on this board. This should just be ignored. Yeah, that should be up and going. Yeah. Welcome to the stream. I hope you can find some entertainment here. I just really want to get this minor thing going, and then we got to sit down and look at this coprocessor, right? So, boom, boom, boom. We go to sources. We go to library. We go to, it's not page. Where is the, oh, it's this coprocessor. Where's this coprocessor reference? Let's go to IP catalog. Get FPGA minor coprocessor, right? Minor processor. So, yeah, let's go look at that guy. That should be nearby here. FPGA minor board. FPGA minor. No, that's wrong. IP repo. Minor coprocessor. HDL. Maybe this one, right? Did they put it in the slave or the master? That is the question. Hash goes in, hash output, so it's going to be in the slave side. Slave side. SHA256 pipelines. Source SHA256. Okay, so yeah, we need to understand SHA256 and what they are doing here. Count total and padded address. Count total, like count total what? K calculator. Block M K calculator. So it's in the functions. So we would have to go to functions. K calculator. Right here. Calculates number of zeros that must be added to the pad meshes defined in some document. Calculates the number of zeros that must be added. So we'll need to go through that process. This board, route design, will be done before we know it. So yeah, we want to understand how this is written, because I can tell you right now, even though this is a, even though they say pipeline here, right? Pipeline. I look at this pipeline instructions, and they just pipelined it into, they have this enable. So when is ready? Ready? Ready if ready equals 0, right? Where is ready assigned high? So ready right here. So to me, this is not fully pipelined. We want to get SHA256 fully pipelined. That sounds like a nasty thing, but we should be able to try to do some improvements. But to do that, we got to understand what this is doing in the first place. We need to go and figure out how the SHA256 is working, then figure out how we can pipeline it into different stages. So we're gonna have to at some point sit down and do like this block diagram explaining all the different little things. So we'll probably have to do another week where we break the SHA-256 down into block diagrams. I need to sit down and read through the algorithm a little bit more. I wish I understood it. Okay, we just finished here. It looks like we are writing byte to bit stream. Then we'll upload it to the HDK, refresh, and go at it. Okay. Do you need a driver to run your design in PL? So what this design is doing is it's using this AXI port. So this is an AXI stream port that's coming out of the microBlaze. I have never used this before at all. So this is how they are sending data, and it's kind of driver software. So they send data packets over here using the AXI stream interface. And if we take a moment and we go to the SDK and we go to the echo here, they are using a command. I think it's this command right here, NOHL, right? Let's go to open declaration. So this is a command for the right. Let's go back there. Oh, right here. Put into blocking data read and write to FSL no ID. So this is writing to that slave port. So if we need to Google that real quick. So microblaze connect to soft processor. Let's see. All right, here we have, so SDK put FSL get F to communicate with ActiveStream IP core. And so they kind of have driver software to communicate. Their driver software is this is how they write to the thing, and then they have a loading bar, yada yada yada, and they get mining results with the get FSLR. So their driver software is very minimal in this situation. I mean, if you're running a true operating system, it won't be this easy. This is running on a standalone bare metal microblaze system, so you're not going to have that main issue of like complicated driver software. But in all honesty, if we're running this in Linux, you could write a very simple Python driver software. You wouldn't use a AXI stream port. You would use a you would use one of the normal AXI ports to load the data, or you would use a DMA engine. And if you use a basic DMA engine, there's plenty of examples with Pink, the Pink Python interface for their Pink OS, whatever, that gives you plenty of examples of how to set up a memory that is continuous and that's continuous, non-breaking, non-cached, and then you can point a DMA engine to that, and then just like this does AXI stream, you can DMA information into this core using kind of the same AXI stream interface. Okay, we gotta export this guy. So let's export this hardware, include bitstream. Yeah, we want to override it. So once we poke this guy, we should see a message soon. That's over here on the other screen. Sorry. Yeah, we'll hit yes. Okay, we're running. We want to wait till echo finishes, and when echo finishes, we'll rerun this and try again. Oh, go back to that screen. Build finish, building or building. This is still the BSP. Actually, no, that's finished. Okay, so we're going to run this again. Programming FPGA. Hopefully the processor. The processor is held in reset. All I can think of is the clock. What clock is driving this? Whatever this clock is, it's not working, right? Why is my sys clock not working? Well, what are you using? Sys clock? I mean, that makes great sense. Clock in. Um, so what we're going to do is just make sure it has the correct bit file, right? So we're going to auto connect here. We're going to program it. And let's go back to the SDK. SDK, maybe you have the wrong bit file. I don't know. I do not know. So you're not programming. You're not doing anything. We're applying that. So we're going to program it through this interface. So we're going to program device. We're going to program, go to runs, implementation, design 1-bit writer. Okay, so we should have the interface. I'm going to show you how to debug this because it was super annoying. Okay, that clock is running. That clock is running. So now I should be able to run this. The microblaze is held in reset. Why is the microblaze held in reset, for crying out loud? I've done what I deem to be sufficient. The M100. Debug, interruption, stop anything. Debugging. ECM locked. We don't really have the locked on the other one. Is this not locking? Okay, let us pull up our debug tools. So we go to SDK. We're gonna pull up this window. Can't really see. You can see well enough. Well, targets. Target. It's held in reset. So if I just do reset of targets, still held in reset. If I do a memory read of the base address 1, 2, 3, 4, what do we get? Okay, this is being held in reset. Let's see if it's the software. Maybe it's the straight up the software, right? The software. So we're going to reprogram it and we're going to check if the processor is held in reset. I don't know why it'd be held in reset, right? Like, what to do? What to do? Yeah, it does the proper mask, right? Right. So targets still held in reset. What is going on? Let's just compare clock configurations, right? Boop. Input clock, right? 100 frequency, phase alignment frequency. Yeah, looks solid. 167, 200, 25. Maybe the DDR clocks are wrong. So we have the 200 is going to clock ref. Clock ref is that. Sys clock is that. Let's check over here. Output clock. One is 166 and 200 is the other one. So 166 there, 200 there. Okay, that looks great. The only thing I can think of is this. Maybe that's it. It's never locking, so it's doing a constant reset on itself. That would explain a lot, you know. And that is causing the reset there. Okay, no, let's just remove the lock signal. Okay, we're doing another revision. It's great. I promise you. Okay, so while we're doing this, let's just review the code. Hopefully that it shouldn't take too long to build. Okay, so anything, this is all IP address. So they copied the echo server, which makes sense. The right one, right? So let's just close all. We're gonna grab this main. Setting up IP server, setting up IP server, setting up DHCP, yada yada. Okay, now we have these registers, and we're not actually using these, so we can just cross those out. EchoNet. So this is all that's really happening in this system. That's fine. That's fine. So we go to Echo S. Yeah. Yeah, we'll figure that out later. So I think this is everything's in the received callback. So everything is in this received callback. This is where they're doing the whole code. To do payload, receive a new block, changing code, doing some separation of into 16 bits. Okay. Generate mask for the packet, given the number of zeros. The number of zeros is a difficulty. This must be something that is in the packet. Packet size. Reduce hash. Sorry, in there. We don't need to worry about loading bar. It's weird that they're using right register. That is the wrong thing to use in that situation. Start loading bar. Nope. Mining count. Digits. Mining count. Step count. We do not need to do that either. Block hex, setting value to remote server, received. There's no interrupt, so I don't know why they're using interrupts in this situation. Right? They have this whole back to here. They have this whole interrupt right here. What's this for the Ethernet? For the Ethernet. Oh, it's probably for the UART and Ethernet. Ethernet. Where's the other one coming from? An AXI timer. Okay, so that's all for the Ethernet. Okay, that makes sense. Okay, we're already back on off design. Okay, so seems pretty straightforward. Let's go back to our hashing. This is still running. That is sad. Oh yeah, validating what the block diagram. We validated the block diagram and didn't really hit the reset. I think it was just a bunch of artifacts from their design that caused the resets to go bad. Oh, okay. For planning. Besides that, I heard that ETH hash, right? ETH hash GitHub was available. Right? Ethereum ETH hash. I want to view the code. Source. Benchmark lib hash. We have hash, ETH hash. That is no SHA-3. Is that what we want? I have to read about how SHA works. So yeah, and next, so after this is that we're going to pipeline. First, we're going to pipeline the SHA-256, and then we're going to pipeline whatever. Ooh, Python, Corsi. Let's go to the README real quick. ETH hash, README. ETH hash, we have a wiki for this. Ethereum white paper. I guess that is as close as we're going to get. Ethereum.org, that white paper. Introduction to Bitcoin, existing concepts. Okay, mining, block. Melco trees, blocking applications, scripting. Ethereum accounts, mergers and transaction messages. Code execution. What is that? See what message we get to be. So we have still have an update there. Good. Blockchain mining. So yeah, so we're gonna attempt to look at the ETH hash, Ethereum hash after this, which will be fun. A lot of things run on the Ethereum network. Okay, let us go back here. Routing is done. Hopefully, we are no longer in reset. So we'll go ahead and program it again. We don't need to reload the code. As soon as we get this done, we'll probably call it a night. This might be, if this finishes by 10, sweet. I will call it an early day. Oh. Yeah. Ah. Sorry, this is not a prepared presentation. I plan to have prepared presentations later, but that is not available at the moment. Oops, there. Okay, back to live stream. Ooh. Current viewer, chat rates, playback. Ooh. Yeah, we are good. So let's go back to hardware manager. No one's really watching at the moment. So, but I'm okay. I am here. I can be participating in my own. Okay. First, let's capture this just to make sure that that's not. I wanted to play no streams 000. Okay, they're all. At least the clock works. That was my main concern. So the clock is operating. Targets. I dare you. What? What? I've done everything I could have. Reset targets. Can we memory read something? 3, 4, 1, 2, 3, 4. It's held and reset. What in the world is wrong with this design? Is this Axie bus that's just like held and reset? Let's just see. That would be part of this thing we just scoped, right? It would be, it's all zeros. We can look at this one too. It's ready. Not valid, like that. So this is going to break me. It's being held and reset. The clock going everywhere. I wonder if that's causing an issue. We want the MIG to be self-isolating. Oh, that's the bus reset. That just issues a reset or something. I don't know. Yeah, let's just go. What's this reset? You have the DRM. Oh. Oh, 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 oh. That's good. And then that one can go there as well. CMC locked. I like that one. Auto, that's good. I do. Did we just scope the debug? Is that what I'm left at? Because I I don't know. I really don't know. I feel like we just need to scope out these guys. Yeah, let's just scope this sucker out. Right here, I want to make external. I want to mark it debug. I want to mark the whole thing as debug. So, this guy right here is our culprit. We're gonna mark you as debug. The whole thing. We're gonna insert an ILA. Yes. We're gonna clock this at the 200 megahertz clock. We have a double speed. What where are these signals going? ILA. Um, oh, and clock automation. Oh, is there a reason each of these were a probe? Okay, first off, why is this not all one probe? Source clock 200. Where was that ILA core? Right here. Let's increase the probes to I don't know. Number of probes. 8, I think. Okay. Uh, Microblaze, auto. I dare you. See if you did you set up another ILA? Yeah, which one is this? Um, Microbug system reset. We're gonna disconnect this pin. First off, it's gonna be we're gonna do the microblaze reset. We're gonna do the bus structure reset. We're gonna do that reset. We're gonna do this reset. We're gonna do slowest clock, external reset, microblaze reset. Do this. We're gonna validate it, rerun it, figure out why this processor is being held in reset because it shouldn't. I don't know why it's being held in reset. Validation successful. Let's generate bit stream. Okay. Check out concurrent viewers. I am going to figure this out tonight, or die trying. I wonder if anyone will join me on my stupid adventure. Oh, I need some water. So, tomorrow is Wednesday. Wednesday is game day. I guess I'll schedule that while we're waiting for this. If there's actually anyone coming on, feel free to ask a question. We are going to do digital game night settings, part 2. Ba-dum, ba-dum. Ba-dum. So we're gonna do Wednesday at 9 p.m. We're gonna go play some games. Oh. Mm. Mm. Should be able to do Thursday too. So Thursday, let's go ahead and schedule a stream, right? Let's go. What is ZCU 104 on any of these pictures? Nope. So we're just gonna grab that one, right? Yeah, reuse settings. Installing Ubuntu on the ZCU 104. Links. So Ubuntu and stylings. I'll use a different picture. Learn how to do Ubuntu on LightX. That'd be crazy, man. Okay, good, finished. Xilinx Ubuntu. Very simple link. Okay, so boom, back to live stream, and that link there. Let's change this to TBD. TBD picture. Next. That's going to be on Thursday at 9 o'clock. We'll see if 9 happens. I might have to delay it a little bit. Okay, I'm doing synthesis, so let's go ahead and watch the log. Ugh. Okay. So let's schedule a stream. Our last stream. Ooh. Oh, Thursday might change up. Yeah, we'll where did that board go? Reuse settings, I guess. Use FPGA boxing, ARIA 10, and Vertex 5. Looking at some use PCIe, FPGAs, FPGAs from eBay. Okay, we're still initializing the design, so let's go ahead and look at that. Feel free to talk or ask questions. I'm just trying to fulfill some of my stuff. Well, yeah. Let's change the picture on that one to TBD. We'll get the boards and put them up. Okay, and visibility, that is planned for Friday at 9, I hope. We'll see. These things may move around. Okay. We are good. Let's go back to our current stream. See if we have any current people actually watching. Oh, do that. Okay. To get around this, we have to go to implementation, log. There we go. Generate those suckers. It doesn't look like. Oh, we had someone spike for a second. That's good. Okay. I will try to fill in the void of me streaming by myself. Oh no, maybe we should throw in a Discord chat. I bet I could throw in a Discord chat and invite people to Discord chat. That might be more interesting conversation. Yeah, let's see. We'll do a poll. We'll schedule a poll for tomorrow. Schedule a poll. Schedule a post. We'll say Wednesday at usually probably want to do it at 8:15 a.m. local time. Poll. Should I add a open Discord chat for live streaming? Anyone join? Yes. 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 Make a new Discord. A Discord. Make a Discord. No. Won't use it. Yes, make a Discord. No, won't use it. Okay, yeah, we'll add that. I gotta say, man, it's really hard talking to yourself the entire time. We have a yo from Pup. I want to go follow your YouTube channel, but that's fine for now. But welcome to the stream. Feel free to ask a question, talk about things. We're just building an FPGA design. The compilation of an FPGA is much longer than software. It's really fun. I'm trying to debug why a processor is in reset. I do not know. Do not know in the slightest. For some reason, this microblaze is in reset. Maybe this reset needs to be reorganized. I mean, that's in the bus truck, right? There, yeah, that's over there. Did the DDR magically fail in this design? Maybe I should remove it and re-add it. So that's that board. But yeah, we are in the route design. How's that going? Implementation, log. Oh, global iteration 0. There might be a little bit of congestion because of all the ILA I added. Okay, good. Probably means timing. Oh, a little rough on the timing. I'm wondering what failed timing. Fix that. The Arty board, yeah, sure. The best example of the open source tools for this board, if we look at Linux on Linux, it talks about no. See, where are the tools? There later. Open OCD. Symny Flow right here. Star. Where is this Symny Flow star? Store. So Symny Flow is what we want to look up. So if we look up Symny Flow, the GCC of FPGAs. start using. Getting started. Semi-flow example. Arctic 7 for the Xilinx. Boom. That's what we're working on. We're working on Arctic 7. We have open source tools. You just have to use SemiFlow. Maybe we'll throw a SemiFlow RD example into the mix, right? Okay. I'm sure there's plenty of examples out there, but let's do another one, right? Does SemiFlow have a logo? I'm just curious if it has a logo. Open image in new tab. SemiFlow. Beautiful. Beautiful, I promise. Okay, so we'll add a SemiFlow. Yes, I will save the image and load it in. So we'll take that picture out. Insert a picture from this device. Yeah, sure. Open source tool. Oh. Um, um, yeah, be careful. Maybe I can outline it. Whatever. We'll work on it later. So this is probably, yeah, we got this good. So let's head over to the hardware open manager. We are going to program this sucker. Sorry, you distracted me. Oh, the first tool. Oh, that was Linux on Linux. So right here, this is a tool for making a software Linux capable RISC-V system on an FPGA. So in this repository, we were experimenting with running Linux on a RISC-V processor. Boom, boom, boom. And they have a bunch of boards that are ready to go. So in like a few minutes, you can have an RD A7 Linux capable RISC-V processor running on an FPGA. It's great. It's beautiful. And it uses, you can also use the open tool flow if you want to. Maybe we can do that. We can do a design by itself. We can do this design. I'll have to pull up my Ubuntu VirtualBox, but we can do it. Boom. So it's programmed, right? This ILA2. Uh-oh. Do we have what I fear? Auto. Vavato crash on me. Okay. Capture right now. Tell me. Okay. What about this one? Does this one trigger? Read again. Okay. That's weird. Did that? Is the HDL top waveform may not be okay. So if I open this block design, right? And we open this guy. Does he have a reset? The input, it goes to reset. Okay, a diagram, reset, active low. So you're telling me Wait a minute. So you're telling me, let's decrease the VRAM usage. Probably run off nothing. Oh, same for all probes, number of comparators. Native interface mix, probe parts, data and trigger. Don't really care. Okay, that's good. Let's open up the old implemented design. It's okay. Need to figure out why it failed timing to go correct that net real quick. And we'll see if we can fix it. Very good. Color scheme. It's just what tool flow ideas can we do? Oh, something like that, maybe. Okay. Yes. Timing. Okay, 10 nets. Intra clock. Setup. Where are these 10 nets failing? Oh, that's all in the pipeline nonsense. Okay. Intra clock. Oh, I'm not worried about that. No, that's fine. That's fine. But design wrapper on the other hand. Okay. Yeah, we'll just not worry about it for now. Generate bitstream. Let's say. One last thing I want to do. Let's keep the sys reset on this, but I don't really like. Let's just remove that addition real quick. Save this and generate. I want this thing to run immediately. Because if that 200 megahertz clock is not running, right? There's no running clock board. That suggests a lot of bad things are happening in the background. Oh, let's go back to our live stream. Pay attention. But yeah, so hopefully this works out well and there aren't much issues. If the processor's not being held in reset, I am going to be upset. But the curious that the 25 megahertz potentially was not working. Oh, we may not be able to share that. Now we should be fine. Synthesis, log, command starting synth design. What is it? I need to get rid of those special board designs for this. Okay. We'll need to. What am I thinking? Probably want to do the new Vivado as well. Gotta go download that sucker. Ooh. Okay, synth design completed. That's great. Not there. There. Ugh, that'll take a while. What can we do in the free time? Get started. Yeah. Flow examples. Install Cineflow and build and upload. Xilinx 7 series. Getting directly to building examples. Series 7 examples. Uploaded design. Counter tests. Sweet. Do that real quick. EcoSot. Light exports, RD Flow. Go RV32. Go come. Cool stuff. Linux Linux demo. Yeah, this is a cool one. Yeah, we just watch this real quick. Go any slower? Swift. Okay, running example designs. Running custom designs. Yeah, they got some pretty good I guess tutorials here. Ooh. Fill and the place design. Steady right. Okay. My patience is waning. Because of that, we're going to do this fun way later. I'm getting my patience is waning. This might be our last build, and I may go enjoy some. Is there anything interesting that's happening that we can investigate? Is there anything FPGA news? News, FPGAs. Lattice general purpose name 2020. Avnet collaborates with digital reality developed tried by high performance cloud-based universal video streaming solutions. I want streaming. I want cloud solutions. What's this thing? Oh, it's very. Okay, let's look up digital reality. I don't know what digital reality is. Um, can you give me FPGAs? That's all I want to know. Um, oh wow, that was so annoying. Cloud, AWS Direct Connect, Platform Digital, SX Fabric. That's what we can usually do. What's usually called. I don't really see. What did they call it? Do, 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 do. Cool. Work on a solution. Visit this site. Okay, that's all I wanted to do. Collaboration platform. Learn more. I want to learn more. Do contact us. That's great. Um, what is on this board, anyways? U30. Alivio U30. Um, Vertex. Probably a Kintex then. Kintex. What FPGA is it? Oh, you didn't. You don't even tell us. Probably like a Kintex Ultra Scale Plus or a Vertex Ultra Scale Plus. They don't tell you. I don't know how much Alivio U30 is. Alivio U30. Yeah. Do they have set price? Contact sales. That's terrible. Why don't you just tell me a price and get it over with? Okay. So let's head back. Finished. Um, do we pass timing? Oh, oh, greatly failed timing. That's okay. We're not worried about timing in this situation. I just want to see the resets. And then I may have to go play around with how they do things. Yeah. ILA2. Do it. The clock's good. Microblaze reset is high. These are low. Okay, so we have a reset. So our DDR is locked. That is low. Flow. Okay, so we have an issue. We have an issue with polarity on these two. If nothing's resetting this, this looks completely valid. Yeah, show me this. I have issues. First off, we're gonna go to this mid control, right? This UE sync reset. Go to properties, config. It's active high. Boom. Great. Now we go to where this thing is, right? Config active high. That's right. Active high. So what's the why is this DMC is locked, microplaces reset is low, right? So I have a mystery on my hands of why this system is breaking like this. So these are all in reset. The clock is running just fine. Like we go, clock is running just fine. Reset is low. Reset is low. MCM is locked. By all accounts, that should be good. I can only think of one thing, and it's tying this to low. Basics or like it's unconnected, right? We should be able to um right aux reset. That is perfectly okay. So what's the best thing to do is straight up delete this clock reset system. Sheesh. I don't know what happened, but that reset was bad. Microplace, what's your current reset? Reset. Are you actually defined? Or are you just like, oh, we're connected, we're chill? Okay. So that clock was running perfectly fine. All we're gonna do is we're gonna go here and disconnect this reset. Connect pin. Should get upset. I guess we'll disconnect this pin as well. Run connection automation. That's a fast clock. Yeah, we're gonna go there. Microblaze, shortest clock, DMC unlocked. And microblaze, debug. It's connected to the microblaze reset. Wow. And the bus struct. Reorganize. The bus struct one was connected to the ILA. Oh, nope. 1, 2, 3. That is this one. Why does it do that? That's clearly there. Good, good, good. What is this? Processor reset. No. Let's make sure these are fed by everything. So all I can say is that we removed something and it did not end well. What are you upset about? Data trigger MCMC lot. Um, third debug. Whoop. Go ahead and generate that bit stream. So that was really confusing. Oh, I would love to go over the Arduino MKR bidder family. So, good question, great question. So, first off, the Arduino, from what I've heard, the Arduino MKR bidder is very, very, very complicated to program, right? So, like FPGA guide for Arduino bidder. Okay, like so here, getting started with FPGAs using. So the process for this is just so complicated. Setting up the basics. Um, so we got this working. When was this last updated? This you have the top file, user file, compile the code, upload the sketch. Last is uploading the sketch to the Arduino. This can be accomplished with Arduino just any on the board the microcontroller the card. You can also use JTAG tags on the board. Okay, FPGA started. Final how this can be accomplished with Arduino IDE. So apparently Arduino IDE already works, right? Oh, there's a GitHub. Um, so let's go. Um, okay, it's right here. Utility to create composite binary for right tools bit stream. Okay, includes FPGA pillar for Arduino family. Source code, projects, things. No. Okay, depending on the quarters two used for compile different versions if you're running analysis. Getting started. No, the step is required only once. Once the start is complete, get a project file, build. We have sample projects. Boom, autonomy of a project, build. Okay, let's see. Let's go through this. Scripts, software, Arduino. Software. Okay, so yeah, this looks fun. Vidor libraries. Vidor FPGA. Um, so yeah, we get an Arduino. We can do that with our that. Let me see. Do I have Vidder on my shopping list? Wish list 2.0, right? Yes, we do have the Vidder 4000 on the list. 3 years ago is a little bit old, but we can do it. Vidder boot. Yeah, I gotta learn how to do Arduino again. Sheesh. Um, but yeah, I just got I've been playing around with Qualtrics or Quartus, not Qualtrics, Quartus. So, oh, okay, we have a hands-on. When was this? This was November 1st, 2018. A little bit old, basic concepts, onto the code. CPU side, percent key to toggle blink light. Okay, yeah. I need to get a board. Think about that. Once we get a video board, we can go through it. That shouldn't be too hard. Be a fun little project to look at. Oh, how are you doing? You are in place design. There, design run, station, log. Okay. But yeah, we could try to go through this. I would need to go find a vidder board, a Vider board. I love the M.2 form factor, right? Um, the M.2 form factor for this board is so interesting. I am not particularly in that country. I don't need that. There's a carrier. That looked like. Overview. Large proto shield. Proto shield. Can shield. IoT carrier. Ooh. So yeah, where are we going? Mini PCIe Express lane. Is that not M.2? Mini, I guess some. Where is the PCIe? Tell me. There's me with up to 25 programmable pins that can own. Mini. What is Mini PCIe Express? I've not seen this before, right? So, Google, educate me. What is Mini PCIe? What is what is Mini right now? Um, is that not M.2? That is M. Is Mini PC M.2? Is this M.2? That two for old lab M.2 to Mini PCIe adapter. Uh, can we go the other way? I want a I want to go the other direction, right? Do do. What's this? Um, I want M.2 to Mini PCIe adapter. What do you got for me? Oh, where's we go? Not that direction. Oh, that's convenient. USB. The other direction. Oh. So a few choices, it looks like. Ugh. I need a I could look like a SATA drive. Let's see. Vidor Mini PCIe connector. Right? People have to have these. Using the pins of the mini PCIe. Oh, you just did a breakout. What if I wanted to plug that into a computer instead of a breakout board? Um, Useless. Want to do the protocol for that? Ah, sheesh. So there you go. Yeah. Vendor tools are that do I say necessary evil? They are very important. Add wave. Make sure this is it's getting bigger every time. Sheesh. Someone needs to kill Vivado. Let's see. Sheesh. Okay, it seems to be working now. So we programmed it. We're gonna do things now. The reset was broken somehow. Sheesh. The question. What was the baud rate on this guy? Design one. Did I change the baud rate on this? UART. UART light configuration. That's the baud rate, all right. Um, Setup. Okay, so we have the software here. So what we're gonna do, we're gonna exit. We're gonna start with I don't want to leave feedback. So what we're gonna do is gonna go to C, X up, do minor 35. We're going to rename that old. Try again. It's okay. It's okay. We're good to go. No. It's not running. I promise you. um, Rename the old. What's stopping you? It's okay. I'm gonna export this again. And launch SDK. Okay. So we have a platform. Beautiful again. No extra nefarious project, application project. We're gonna do a hello. I guess we'll do echo. Or why not? Hello world. Echo server. So, the serial port is not working so far. That is bad. But we'll get there. We'll get there. We'll figure it out. So console. As soon as it's done running, PSP is we're good to go. So we're gonna right click this. We're gonna say run as launch on hardware. Um, That is beautiful. Okay, now we're gonna do a new application project. We're going to call this minor. We're going to use existing that one. And we're going to do an empty application. And source, we are going to import a general file system. Browse. We're going to go to this PC, I guess. C, except minor. Old FPGA minor source. And select all. Yes, do all. We can regenerate it. I'm not too worried. Echo. What's the issue? We have yeah, we don't need no GPIO. Oh. Nope. Don't need no GPIO. Why are they running that in? How's the main just do it? Echo BSP. What do you have issues with? Why did that fail? That's weird. Hmm, hmm. Regenerate BSP sources. Okay, let's just try to delete this. Yeah, we'll have cloud stuff just fine soon. So what we're gonna do is we're gonna copy this over and just change file by file. Okay. File, new application. We're gonna call this minor again. Mine. Yeah, mine. We are going to use that one. We're going to use echo server. Finish. So proper references. So what we're gonna do is we're gonna go old FPGA minor source. Boop, boop. Edit. Don't need that. You know what? Let's actually keep this the same. I want to see the differential. Let us do a good difference of these. So open. I want to open SDK. Line source name and move to other view. Let us do a compare, please. Compare. Yeah, what's all this garbage? No, we don't need to worry about that. We don't need that. Nope. Yeah, it's fine. It's fine. It's fine. Okay, so really, let's just bring this over. Otherwise, it's all the same. Okay, see ya. Have fun. Feel free to join later or join another day. Okay, now we want to compare the echo. So we're going to close all but this. Yeah, but so this is this SDK. We're gonna open echo. We're gonna open old FPGA miner source echo and move to other view, and we're gonna do compare. Um, okay, so we hit up echo, right? And it's going to be this and the receive callback. Yeah, the entire receive callback. Bang count undeclared. Where is my H file? All right, there. Up above transfer data. Whee. Okay, so it seems to be working. So we're gonna go ahead and run as launch on hardware. Yeah, that's fine. Okay, so oh, that did not talk about hash rate. Um, uh, okay, so we want to open it up another window here. A PowerShell window here, and CPU test. First off, let us results. Um, there's the time to do that, I guess. Okay, and then we need to edit server. Server. We are doing 8. Not that different. Yeah, so we'll just do Python server. Python 3 server. Connecting to FPGA. Um, okay, that would kill it. Whoa, guys, we're hashing on an FPGA. Okay, first off, let's go back to this guy. Why CPU test do you so you are what doing 10 10 and server for difficulty. Okay, so so we're gonna do control, setup terminal down here, receive, we're gonna do auto. And then over here, back to SDK, let's go to our settings, run configurations, mind, I want you to program, reset the entire system, apply, run. Programming. Okay. Okay, let's go. So how can I say that it's much, much faster? So how do we convert this to hash rate? Or like, right? Let's see, what's the software say? Broken elapsed time divided by counter. Let's go check out this GitHub FPGA. Okay, right? FPGA miner. Yep. Here's our coprocessor. Um, $14 per block. Guys, we can mine. So, oh man, yeah, it's going much faster. What was the difficulty we put on this guy, right? And zeros. Oh, okay. Let's make this fair. Okay. So, okay, that's done. Let us, is there a way to clear this? Clear. Clear. So we have the same difficulty now. We're gonna go ahead and program a sucker. We're gonna have a race. Who can do the most blocks? Do they calculate in their code? Elapsed time. Server. Um, won't really discuss anything else. Okay, so this is going to be a little bit iffy, but let's try. Enter, enter. Um, That's a fun race. Okay, that's cool. Let's check out our utilization. Design right here. Boom, utilization. We actually have a good luck thing. Well, we should do a breakdown of our implementation. Open design. Yeah, we can do it. Report utilization. It's close enough. Yeah, we should use software to time these things. Yeah, we should be able to get this hash rate up crazy. So we go back to this guy, right? What is my design taking up? Boom, give me the slices. Give me the slice of light. No, that's wrong direction. Slices. Oh, we can get rid of that. We can get rid of that. Ooh, coprocessor, only that much. Remember how many blocks do we have? We can do so many coprocessors. We can do so many. Oh, it's only 350. We could get that up to 1 meg hash. We could do 1 meg hash. Man, if we could do 1 meg hash. Oh, that's easy. Oh, okay, guys, we could go crazy. Now we just gotta figure out how to do ETH hash. Okay, I love it. I love it. Good night. I'm sure no one's watching me, but that's okay. That's okay. We are going to make mining on FPGAs fun again. Or I don't know. It's great. Okay. Good night. Enjoy the FPGAs. We can, with that much utilization, we can go crazy or learn how to pipeline it more. There's a difference between like parallelize it or pipeline it more. We could easily have everything grab that those things at the same time. We could. Yeah, we could do a lot of. Very stream mode. Okay, but that is it for tonight. Good night. We did hashing on an FPGA. We did it. We did it. Hashing on an FPGA was so much fun.